Hello everyone, in this video we'll be solving a medium problem 909 snake and ladders. The problem statement is we are given an n by n integer matrix board where all of the cells are labeled from 1 to n square in a bootstrap-hidden style.
We need to return the least number of dice rolls needed to reach the last square, that is n square. Let me quickly explain the rules for those who are not familiar with the board game Snakes and Ladders. It is a multiplayer game where the players play on an n by n board. The aim is to reach the last cell the quickest. On their turn, each player will roll the dice and move that many spaces on the board. To make game interesting, there are ladders and snakes on the board at random squares. If you reach to the bottom of the ladder, you can take that ladder and reach to the top of it. And then there are snakes. If you land on that square, it will take you back several spaces. Hopefully you're familiar with the game rules. The problem statement is asking us to identify the minimum dice rolls needed to reach to the last cell. In example number 1, the minimum number of dice rolls needed to reach to the last cell is 4. The player starts at cell 1. At that point, the player needs to draw 1, which will take them to 2 and take advantage of the ladder. The ladder will take us to 15, and from that point we need to score 2 on the dice, taking us to 17. And there is a snake on 17 which will take us back to 13. From 13, we'll score 1 on the dice, taking us to 14, from where we can take the ladder to reach 35. And from 35, we only need 1 more to reach to 36. Overall, we only needed 4 dice rolls to reach to the last cell. There are certainly other possibilities to reach to the last cell, but this is going to be the shortest path. I hope this walkthrough was helpful. Now let's switch to whiteboard and discuss how we can solve it.
As usual, we'll try to solve this problem using a brute force approach. In this approach, we'll try to identify all possible combinations from the first element to the last element. Because we are going to roll a dice and the only combinations that are available is 1 to 6,
We will try all possible combinations. In other words, we are trying to build a graph or a tree where the current cell becomes the parent with 6 legs. Let's do a quick dry run with the first element as 1, with 6 legs, as there are 6 possibilities if you roll a dice. Depending on the dice roll, I will reach a different cell every time. For 1, I'll reach 2. If I roll a 2, I will reach the cell 3, and so on and so forth. It is also possible that one of these cells can land me on a snake or a ladder. If that were the case, instead of saving the original cell value, I will replace it with the destination where the snake or ladder will take me. For instance, if I reach cell number 2 where is a ladder, it will take me to 15. So instead of writing 2, I will write 15 over there. Remaining cells do not need any updates because there are no snakes or ladders, so we'll leave it as is. These are the cells I can reach when I roll my dice for the first time. As I have not reached the last cell, I will roll the dice again. We will have to do the simulation for all the cells. Let's start with 15. These are all of the values after rolling the dice second time. One of the legs take me to 17, which is ahead of the snake. So instead of staying on 17, it should take me to 13. So I'll replace that value with 13 in this formation. I will repeat the same cycle of identifying the next leg, that is rolling the dice second time, from the cells that I reached on the first roll.
this process will continue until I reach 36, that is the last element.
And as we are building this graph, we will also be maintaining the number of dice rolls needed to reach to the destination, that is the last cell. This is because we want to return the minimum number of dice rolls needed to reach to the last square. With this solution, the time complexity is going to be O of 6 raised to power d, where d is the longest path from start to finish.
And
The
trying
time
all possible
complexity is high
combinations to
because we are trying all
identify the
possible
minimum number of
combinations
dice
from
rolls
1 to
needed
all
to
the way
reach
to
the
6
last element,
for each
while the
cell
space
that will take
complexity
us
is
to
going to
last
be O
element,
of
that is
1.
36. While the space complexity is O of n square, as we are running recursion stack, which requires some memory to maintain its state. Let me highlight the issues with this approach. Let's assume we are at square 3 and we want to roll a dice. So there are 6 possibilities which can take us from 4 all the way to 9. If you observe carefully, few of the cells we can already reach with a single dice roll, starting with 4 all the way to 7. So it doesn't make sense for us to reach to the same cells using two dice rolls as we are looking for the minimum number of dice rolls. The same will happen when we are at cell 4 and we are trying to identify the next 6 combinations. We need to figure out a way to avoid processing the same cells multiple times if it has already been visited. Keeping that in mind, let's discuss how we can optimize our solution.
One way to improve our solution
Is to do BFS traversal on the graph that we were trying to build earlier while recording all of the cells that we have already visited to avoid duplications. Maintaining the cells that we have already visited will help us optimize our solution by several folds as we don't want to process them multiple times. As we want to do a BFS traversal, queue is the best data structure that we can use as it offers first in first out. And as we only want to know if the cell has been visited, we can use an array of type boolean where we'll mark each of the cell as true once it is visited. Let's do a quick dry run to understand how these two data structures will help us optimize our solution. When we start the game, each player begins at position 1, that is cell 1. As we can reach a total of 6 cells after this point, we'll mark all of them as visited and add it to the queue. And as we discussed earlier, if any of the cell is part of a ladder or a snake, instead of saving its original value, we'll save the new value where it will take us. In this case, we will not be saving 2 as it is part of a ladder and instead save 15. And as we are using BFS with a queue data structure, we'll do first in first out. So the next cell that we need to process is 15. Let's add all of the possible cells we can reach after 15 into the queue and also include it in the visited. As there is a snake at 17, I will not write 17 and instead write 13. As 15 is processed, I will remove it from the queue and move on to the next element, which is 3. From 3, we can reach cell 4 onwards 9. But few of the cells are already marked as visited in the array. So instead of adding them, we just skip it and only add the ones that are not yet visited. Only 8 and 9 will be added to the queue while marking them as visited. Removing 3 from the queue and moving on to the next cell, which is 4.
from 4, I can reach anywhere from 5 to 10, but all of the elements from 5 to 9 are already been added. So we'll only add 10 to the queue and mark it as visited. Similarly, we continue to iterate through all of the elements in the queue until we reach to the last element on the board. With this solution, our time complexity is improved to O of n square, while the space complexity is also O of n square, as we are using two collections, one to store the elements that we will be visited next, and the second to store the elements that we have already visited. There is one more challenging aspect to this problem which we have not yet talked about. The challenge is to determine the x and y coordinates, that is the row and column for each cell. So far, we have been talking in terms of cell number, but when we are actually writing the implementation, we need to do a lookup on a two-dimensional array to identify what is the cell value. It is needed for us to know whether the cell is part of a ladder or a snake. Because the board is of a booster fidden style, where the direction in which the numbers are added is not the conventional way, we need to make sure our logic also handles it well. We can't just use the mod and division operation to calculate the corresponding value on the grid. In a conventional grid, the numbers start from the top left corner and moves towards the right. But here we are starting from the bottom left and moving towards the right in the upwards direction. And for each row, the direction in which we are moving is changing, either from left to right or right to left. So we need to take all of this into account when we are writing the implementation. Let's try to figure out a pattern using these two numbers, 9 and 28. Conventionally, if we want to calculate its row, we will do square minus 1, that is the value minus 1, because it is a 1 indexed array and not 0 index, and divide it by n. With the cell or square value as 9, the result will be 1. That is, the 9 exists in row 1. But if you look at the board, 9 is not the first row, it is actually in the second last row. So we need to modify the conventional formula to make sure it applies to this kind of problem. Because this is an inverted board where we are starting from the last row and moving upwards, we should subtract row from n minus 1 to get the real output. We are doing n minus 1 because it is a 1 index array and not 0 index. With this modification, the actual row will be 4.
Let's apply the same logic for square 28. Based on the conventional formula, row will be 4. Using row is equal to 4 in the updated formula, we will get 1. So 28 should exist in row 1. Now let's discuss how we can calculate the column value. The conventional formula to calculate column is square minus 1 and then apply the mod of n operation on it. Using this formula for square 9, the row column will be 2. And for square 28, the column will be 3. If you compare these values to the actual position of 28 and 9 on the board, you will see the value of 28 is correct, but for square 9 is incorrect. This is because of the direction of the row. If it is moving from left to right, the conventional formula will work. But if it is moving from right to left, the conventional formula will give us incorrect results. If you look at all of the columns which are not following the traditional direction, that is moving from right to left, are all even rows. We can use the even odd logic to determine which formula to use to calculate the column value. Similar to the formula that we use to calculate the rows because of the direction, we'll apply the same logic here. When we are looking at a row where the direction is from right to left, instead of taking the column value directly using the conventional formula, we'll subtract it from n minus 1.
As column 9 appears in an even row, we'll use the new formula resulting in the column as 3. As 28 is in an odd row, we don't have to apply the new formula. I hope you were able to follow the logic we use to calculate the x and y coordinates for each square. Let me show you how we can implement this using C#. In this C# implementation, I've created this helper method getCoordinates which accepts the square, that is the cell value, and returns the x and y coordinates in the array format. It uses the same logic that we discussed earlier to calculate rows and columns, and depending on the row being odd or even, it will use additional formula to calculate the column value. In the main method, I've initialized couple of variables to record all of the cells that we have already visited and the cells that we will be visiting next. After initialization, I'm pushing 1 to the queue as that is the starting cell where the game begins. After marking 1 as visited, I'm initializing a new variable moves that will record the number of dice rolls needed to reach to the last point. After that, I'm starting a while loop until queue is not empty. Inside the while loop, I'm running a for loop to iterate through all of the cells that have already been added to the queue. Inside the for loop, I'm removing the first element from the queue and checking if is it the last element of the board. If yes, then we reach the end, so we can stop the iteration and return moves as the output. If it isn't, then I'm running a for loop to try all possible combinations of the dice roll, that is from 1 to 6. Inside the for loop, I'm adding the dice value to the current cell to get the next cell and then checking if it is greater than the n square, that is the end cell of the board. If it is greater, then there is no point continuing with the loop, so I'm just breaking out of the loop and trying a different combination. Once we have confirmed that the next position is valid, I'm calling the getCoordinates method passing the next cell to get its row and column value. If the coordinate of the next cell is not equal to -1, it means it is either a ladder or a snake, so I'm replacing the next value with the value in the two-dimensional array for that corresponding row and column. Before adding the next cell to the queue, I am first checking if it is already visited. If yes, then we'll skip the step or else mark it as visited and then add it to the queue. Once the outer for loop completes, I am incrementing the moves by 1 because all of the elements that were added after the for loop started is part of the next dice roll. Hence the move needs to be incremented by 1. If we did not find any valid way to reach to the last cell and the queue is empty, we will jump out of the while loop and return -1 as the output. This code, when submitted on LeetCode, beats 68% of the submissions in terms of runtime and nearly 15% in terms of memory. Thank you for watching this video. I hope you are able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out and I will see you in the next one. Thank you.